Good day! This is a presentation for Getting Real with Real Number by the Team Negros. Sir Lesser Luke, Miss Neri Garinganao, Mr. Alfie Silva, Sir Mark Xavier Guanzon, and yours truly, Kirsten Craig. Question: what are real numbers? So if we want to describe what are real numbers, we can also try to see the examples of different kinds of numbers. So let's try. So the first line, 1, 2, 3, 4, 5 refers to examples of natural numbers or counting numbers. The next example, 0, 1, 2, 3, 4 are example of the set of whole numbers. The third example are integers. Fourth example are rational numbers. The last example are irrational numbers. So what does this relate with the real numbers? Simply, all the sets indicated below are considered real numbers. What are real numbers? A real number is a number that can take any value on the number line. So a real number can be any of the rational and irrational numbers, or either integers or counting and whole numbers. Just like this.
On this slide, we will discuss about field actions. Set S with operations addition and multiplication is a field if and only if the following properties hold true for all x, y, and z elements of the given set. These properties are closure property, associative property, commutative property, identity property, inverse property, and distributive property. Now, let us identify if the set of real numbers is a field. First, let us find out if R, or the set of real numbers, is closed under addition and multiplication. The set of real numbers with operations addition and multiplication is a field if the following properties hold true for all A, B, and C elements of R. If for all elements A and B, elements of the real numbers, there exists A plus B, which is an element of R, and A times B, which is also an element of R, then R is closed under addition and multiplication. This means that the sum or product of any two real numbers will also result to a real number. Now, let us find out if the set of real numbers is associative under addition and multiplication. For every element A, B, and C, elements of the real numbers, there exist A, B, and C such that quantity A plus B plus C is equal to A plus quantity B plus C, and quantity A times B times C is equal to A times quantity B times C. Then, the operation is said to be associative in the set of real numbers. For example, if we let A equals 2, B equals 4, and C equals 7. Let us find out if the associative property holds true in this example. Example: quantity A plus B plus C is equal to A plus quantity B plus C. Substituting the value, we have quantity 2 plus 4 plus 7 equals 2 plus 4 plus 7. Then, solving the parentheses, we have 6 plus 7 equals 2 plus 11. Then 13 is equal to 13. This means that R is associative under addition. How about in multiplication? For example, quantity A times B times C equals A times quantity B times C. Substituting the values, we have quantity 2 times 4 times 7 equals 2 times 4 times 7. Performing the parentheses, we have 8 times 7 equals 2 times 28. Therefore, the answer is 56 equals 56. This means that the set of real numbers is associative under multiplication. How about the commutative property? For every element A, B, and C, elements of the real numbers, there exist A and B such that A plus B is equal to B plus A, and A times B is equal to B times A. Then, the operation is said to be commutative in the set of real numbers. For example, if we let A equals 3 and B equals 9, then A plus B equals B plus A. Substituting the value, we have 3 plus 9 equals 9 plus 3. Solving, we have 12 equals 12. Therefore, the set of real numbers is commutative under addition. How about multiplication? We have A times B equals B times A, then 3 times 9 is equal to 9 times 3. Solving, we have 27 equals 27. Therefore, R is commutative under multiplication. How about the distributive property? For every element A, B, and C for the set of real numbers, there exist elements A, B, and C such that A times quantity B plus C is equal to quantity B plus C times A. Then, the operation is said to be distributive in the set of real numbers. For example, if we let A equals 3, B equals 6, and C equals 8, then A times quantity B plus C equals quantity B plus C times A. Distributing, we have A times B plus A times C equals B times A plus C times A. Substituting the values, we will have 3 times 6 plus 3 times 8 equals 6 times 3 plus 8 times 3. Then, 18 plus 24 equals 18 plus 24. Therefore, 42 equals 42. This means that the set of real numbers is distributive under multiplication and addition. Does the set of real numbers have an identity element? For every element A, B, and C, there exists an element E such that A plus E equals A and A times E equals A. Then, E is the identity element in the set of real numbers under addition and multiplication. For example, if we let A equals 10, then A plus E equals A. Substituting, we have A plus E equals 10. Then solving for E, we have E equals 10 minus 10. E equals 0. Therefore, 0 is the identity element of R under addition. How about in multiplication? A times E equals A. Substituting, we have 10 times E equals 10. Solving for E, we have E equals 10 over 10, which is E equals 1. Therefore, 1 is the multiplicative identity of the set of real numbers. Does the set of real numbers have inverses? For inverse property, we have for every element A, B, and C, elements of the set of real numbers except 0, there exists an element A prime such that A plus A prime equals 0 and A times A prime equals 1. then A prime is the inverse element in the set of non-zero real numbers under addition and multiplication. For example, we let A equals 10, then A plus A prime equals 0. Substituting 10, we have 10 plus A prime equals 0. Solving for A prime, we have A prime equals 0 minus 10. Then, A prime is equal to negative 10. Therefore, negative 10 is the additive inverse of 10. How about multiplication? 10 times A prime equals 1. Solving for A prime, then we have A prime equals 1 over 10. Therefore, 1 over 10 is the multiplicative inverse of positive 10. Does the set of real numbers have zero divisor? Set R has no zero divisor if and only if cancellation law holds in the set of real numbers. Suppose cancellation law holds in the set of real numbers such that A times B equals A times C, then B equals C. Take note that A should not be equal to 0, such that A times B is equal to 0 for all elements A and B of the set of real numbers. Since A times 0 is equal to 0, thus A times 0 is also equal to A times B. By cancellation law, we have cancel A, therefore B is equal to 0. This means that the set of real numbers has no zero divisor. Now that we have proven that all the 7 properties has been satisfied, therefore we can conclude the set of real numbers is a field.
Now we are going to talk about the principle of mathematical induction. So what is the principle of mathematical induction? It's actually a method of writing a proof. So it's a technique of proving a statement, theorem, or formula which is thought to be true for each and every natural number n. By generalizing this in the form of a principle, which we would use to prove any mathematical statement, it is called as the principle of mathematical induction. Let's try to put it into context. Consider a statement P of n, where n is a natural number. Then, to determine the validity of P of n for every n, use the following principle. So these are the steps in using the principle of mathematical induction in proving a particular mathematical statement. So step 1, we check whether the given statement is true for n equals 1. This will be our first step. And then after that, we make an assumption. We will then assume that given the statement P of n is also true for n equals k, where k is any positive integer. Step 3, after assuming that n is equal to k, let's prove that the result is also true for P of k plus 1 for any positive integer k. If the above mentioned conditions are satisfied, then it can be concluded that P of n is true for all n natural numbers. Now let's have an example. In proving using mathematical induction, the first step of the principle is a factual statement, and the second step is called a conditional statement or an implication. According to this, if the given statement is true for some positive integer k, only then it can be concluded that the statement P of n is valid for n is equal to k plus 1. This is also known as the inductive step. When we talk about inductive step or the process of induction, we always start from specific to come up with a general conclusion. And the assumption that P of n is true for n is equal to k is known as the inductive hypothesis, or shall we say it's the inductive premise for us to come up with a conclusion. To put it into actual situations, let's try to prove this particular mathematical statement. Let us show that the sum of the first n odd integers or positive odd integers is n squared, or 1 plus 3 plus 5 and so on and so forth until 2n minus 1 is equal to n squared. Take note that 2n minus 1 there signifies the nth odd integer. For step 1, we need to show that it is true for n is equal to 1. So if we substitute, or if we try to find the sum of the first one positive odd integer, it's simply 1. It's basically equal to 1 squared. So that is true. Step 2, we assume that it is true for n equals k. So this will be our inductive hypothesis. So this is merely an assumption. So 1 plus 3 plus 5 and so on and so forth, instead of writing 2n minus 1 there as our representation, we use 2k minus 1 to represent the kth odd integer. And that shall be equal to k squared based from our step 1. Now, after coming up with that particular assumption, we need to check for n equals k plus 1. You can see right here in our process, the left-hand side of the equation, we have here 1 plus 3 plus 5 and so on and so forth. But instead of just writing the 2k plus 1, we replaced it with k plus 1. So k plus 1 minus 1, which is actually just the next term after 2k minus 1. If we're trying to come up with a sequence of the first n, or the first set of positive odd integers, the next term after 2k plus 2k minus 1 is 2 times quantity k plus 1 minus 1. So that's it. That will be equal to k plus 1 squared. And then, since I mentioned that this is just the next term of 2k minus 1, that means somewhere here, we have the 2k minus 1. So I can just write it so that I can relate it to the previous equation that we had earlier. And then notice that this particular part right here represents our inductive hypothesis that was in the previous slide. 1 plus 3 plus 5 and so on plus 2k minus 1 is equal to k squared. So instead of writing that, I replaced it with k squared. And then I just copied the remaining parts of the equation. Now if I'm going to simplify both the left-hand side and the right-hand side of the equation, multiplying this or distributing this, 2 times k is 2k, 2 times 1 is 2. So I just copy the k squared, 2 times k is 2k. Then since I have here 2 times 1, that's 2 minus 1, will be left with 1. So k squared plus 2k plus 1 will be equal to our right-hand side of the equation, which, if I'm going to expand that binomial, will also be equal to k squared plus 2k plus 1. So notice that in that process, we were able to prove that the left-hand side of the equation is equal to the right-hand side of the equation, which indeed proves that if it is true for n equals k, and it's also true for n equals k plus 1, then by principle of mathematical induction, we were able to prove that indeed the sum of the first n odd integers is equal to n squared. The result is true for n equals k plus 1. We see that the given statement is also true for n equals k plus 1. Hence, we can say that by principle of mathematical induction, this statement is valid for all natural numbers n. This principle can be used to prove different mathematical statements that involves sequences, that involves binomial expansion, and many more. This is a very interesting topic, and this is probably one of the foundational topics in number theory, which we will also need in coming up with investigations in our real analysis subject. Thank you very much for listening.
Good day, everyone. Today, I will discuss to you one of the important number property called dual ordering principle. What is a well ordering principle? The well ordering principle states that in every non-empty subset of positive integers contains a least element. Let's consider this positive integers first. When we say positive integers, of course, this can be also called as natural numbers. And it's very obvious that the least elements contained in this given set is 1. How about considering another set of integers that is greater than or equal to 4? Of course, it's very obvious as well that the least element is 4. However, for the set of rational numbers, is the set of rational numbers contains a least element? The well ordering principle says it does not have, or it has no least element. Always remember that the well ordering principle is true only in natural numbers, but it's not true when you consider the integers, the rational numbers, the real numbers, or the complex numbers. Let us look at more in detail what well ordering principle is. So let A be a set such that the following conditions satisfy. A is a subset of natural numbers, and second, A is not an empty set. So given these two conditions satisfied by the given set A, then there is a natural number M such that this natural number M is an element of A. It means that the natural number is on set A or in the given set. And second, M is less than or equal to A for all A elements of set A. Basically, what we are saying here is it has a minimum. The given set has a minimum. Or the important of this is the minimum has to be in the set A. So now let's look at an example and let's see how this will work. Let's start with example number 1. If we consider set A containing the elements 3, 6, 8, 11, and 23, let's check if the two conditions satisfy. Yes, we have here start with 1. The given set is a subset of natural numbers. That's true. Also, the given set is not an empty set. So by well ordering principle, set A has a minimum. And it's very obvious that the minimum elements of set A is 3. That's an easy example. Now let's go to the second one example. We have here set A is a set of all n elements of n natural numbers such that n squared plus 3n minus 200 is greater than 0. We need to check if the two conditions satisfy in the given set. Of course, it's very obvious that set A is a set of natural numbers because it is stated that n, or the elements, is on the natural numbers. And second, to check if this is not empty, how are we going to do it? Of course, by simplifying n squared plus 3n minus 200 greater than or equal to 0, we can find the value of n. Then we need to replace it to the inequality. And after that, let's see if it contains the elements. Okay, actually, for instance, if we're gonna calculate it, we know that one of the elements in the given set is 100. 100 is an element of set A. This satisfies the second condition that A is not an empty set. So therefore, the given set by the well ordering principle has a minimum. The third example we have here, set A is set of n elements of n natural numbers such that n times sine 2n or sign times 2n is greater than 8. Let's see. Let's check if the two conditions satisfied in the given set. For set A, for first condition we have A is subset of natural numbers. Yeah, it's true because it is given. It is stated in the description of this set that the n is an element of natural numbers, or the elements of the given set are elements of natural numbers or subset of natural numbers. The second condition we need to prove, we need to satisfy, to justify that set A is not empty. And let's see how we're going to do that. Of course, you may solve the inequality and then substitute the value of n if the resulting elements are really greater than 8. Or we can numerically actually check, to make it fast, we can numerically check that 13 is really an element of 8. Simply substitute it to n and then solve, and then you will come up with a value that is greater than 8. So by well-ordering principle, the two conditions are satisfied, so automatically this given set has a minimum. And let's have the last example. We have set A contains n element of natural numbers such that n is equal to x squared minus 8x plus 12 for some x such that element of set of integers. So let's check again if the two conditions or the two properties of well-ordering principle satisfied in this given set. Let's start with the first one. A is a subset of natural numbers. That's true. It is defined that n elements of this set A is a subset of natural numbers. So satisfied for condition number 1. For number 2, A is not an empty set. How will you know that the given set is not empty? You may solve n is equal to x squared minus 8x plus 12. And then by factoring, you will come up with a value of, I think we have 1 and 7. And because it's not empty, therefore, by well-ordering principle, we can say that the given set number, for example, has a minimum. And actually, if you're going to simplify it, the smallest element there is 5. So that's all about the well-ordering principle. Again, we need to check if the given set is, or a given set is a subset of natural numbers, or if the second one, if the given set is not empty. Before I'm going to end, I would like to share this quote. Sometimes the smallest step in the right direction ends up the biggest step in your life. So those least elements in a given set is very important. We need to know that because actually they are part of our least element is very important, especially in mathematical induction. So the same with this one, if we're going to relate to this code, and every smallest step that we have really affect, or sometimes it ends up the biggest effect in our life. And that's all for today. Thank you for listening.
Hello, classmates. So this is the continuation of our presentation on real numbers. At this section, can you at least choose any number? Whatever number that comes into your mind. Let's say you have chosen the number 13. If you chose this number, be it known that there is another greater number, let's say, or 19. And for the number 19, we have another greater number, let's say 45. And for 45, we have another greater number, 56. And so on. If you observe, the numbers written here is in ascending order. Meaning, the prior number is always lesser than the next number, or if we state that the next number is always greater than the prior number or the preceding number. Let's have another example. Let's have this comparison of heights. We have the apple tree, the 10-story building, the giant sequoia, and the coast redwood. So if you can see the apple tree and the 10-story building, we can compare that the 10-story building is greater than the apple tree. And then, even for us who is the 10-story building, then we are beside a giant sequoia, we can see that the tree is much taller than the building. And then, for the giant sequoia, beside the coast redwood, we can see that the coast redwood is greater than the height of the giant sequoia. So where does this lead? So those are simply an example of the Archimedean property. So what is an Archimedean property? So we have here the theorem: if A and B are positive real numbers, then there is a positive integer Q such that the product of Q and A is greater than B. To illustrate, we have set A as the red line and B as the green line. Then if we combine this, we can see that each red lines, when put beside the green lines, they are lesser than the green lines. Restating this, we can say that for every red line, there is always a greater line. Or simply, the product of Q and A is greater than B. Okay, so let's prove this property. Using the concept of the well-ordering principle for the positive integers, given a real number x, there exists a unique integer q such that q is the greatest integer less than or equal to x. Since b over a is greater than 0, then 1 plus b over a is also greater than 1. And the integer q defined by q is equals to 1 plus b over a, such that q is greater than or equal to 1 and q is less than or equal to 1 plus b over a, q plus 1. Therefore, q is greater than 1 plus b over a minus 1 equals b minus a. Multiplying by the positive number a gives q times a is greater than b. For equivalent statements, we have the first one. It's a subset of R, or the real number. The set C plus, for the integers, positive integers, is unbounded. For each element Z, as an element of R, there exists an element of Z plus, such that n is greater than Z. For each AB as an element of R with A greater than 0, there exists an n as an element of Z plus such that n times A is greater than B. And the last, for each A element of R with A greater than 0, there exists an n as an element of Z plus such that 1 over n is greater than 0 but less than A. That's for today.
Good day, everyone. I am Sir Alfie, and I am going to discuss with you the concepts of lower and upper bounds and also the infimum and supremum. Let us start with lower bound and infimum. To begin with, let us illustrate the set of real numbers using a number line, and we'll let p be a real number. Then we'll let m be the subset of real numbers such that the elements of set m are real numbers greater than or equal to p. Set m is said to be bounded below, and we can identify its lower bound. So what are the lower bounds of set m? We let m be a set of real numbers. A number a is a lower bound of m if and only if m is greater than or equal to a for all m elements of set m. In other words, a lower bound should be less than or equal to all the elements of set m. A lower bound of a set is not unique. Hence, we can identify several lower bounds of set m aside from a. In fact, all real numbers in color red are lower bounds, including p, which is part of set m because we have the condition greater than or equal. A lower bound of a set may or may not be contained in the given set. If it is contained in the set, then it is the minimum value of the set. In this example, m minimum is equal to p. However, if p is not contained in the set, p is still a lower bound of m but not the minimum value of m. The greatest among all lower bounds is called the infimum. There are two conditions that should be met for a real number to be an infimum of a given set, say set m. First, infimum of m is a lower bound of m, and it should be greater than or equal to every lower bound of m. In this set, p is the infimum, and since it is a part of set m, it is also the minimum of m. Thus, if the set has the least element, m minimum, then the infimum of m is equal to m minimum. Let us now proceed with upper bound and supremum. Again, let us illustrate the real number using a number line, and we'll let p be a real number. Then we'll let m be the subset of real numbers such that the elements of set m are real numbers less than or equal to p. Set m is said to be bounded above, and we can identify its upper bound. How do we find the upper bound of set m? We let m be a set of real numbers. A number b is an upper bound of m if and only if m is less than or equal to b for all m elements of set m. This means that the upper bound is greater than or equal to all the elements of set m. And similar to the lower bound, we can also identify several upper bounds including p. All the numbers in red are upper bounds of set m. An upper bound may or may not be contained in the given set. If it is contained in the given set, then we can say that it is the maximum value of the set. Since p here is part of set m, then we can say that it is the maximum value of m. If p is not part of set m, it is still an upper bound but not the maximum value of m. The least of all the upper bounds is called the supremum, and there are two conditions that should be met for it to become a supremum. First, it should be an upper bound of m. Second, it should be less than or equal to every upper bound of m. So in this set, p is the supremum, and since it is part of set m, it is also the maximum value of m, or m max. Thus, if the set has the greatest element, m max, then the supremum of m is equal to the maximum value of m, or m max. For more clarity, let us have some examples. First, let us have the set m from 3 to positive infinity. Since set m is bounded below, we can identify its lower bound. So what are the lower bounds of m? So the lower bounds of m are 3, 2, 1, 1.5, and so on. Take note that a lower bound may not be a whole number. Then, the m minimum, or the minimum value of m, does not exist. It does not exist because 3 here is not part of set m. But the infimum of this set is equal to 3 because 3 is the greatest of all the lower bounds. Let us have our next example. We have the set from negative infinity to positive 5. This set is bounded above, so we can identify its upper bound. So what are the upper bounds of set M? So we can have 5, 6, 6.5, 7, and so on. The value of M max, or the maximum value of M, is equal to 5 because 5 is included in the set. It is also the value of the supremum because it is the least value of all the upper bounds. So in this example, since 5 is part of the set, the value of M max is equal to the value of the supremum. For our final example, let us have this set, negative 2 to 4. This set is called a bounded set because it is bounded below, at the same time it is also bounded above. So for this example, we will identify both the lower bounds and the upper bounds. Let us take first the lower bound. So the lower bounds of M are, we have negative 2, negative 3, negative 4, negative 4.5, and so on. Our M minimum, or the least value of M, is negative 2 because negative 2 is part of the set. Our infimum, which is the greatest of all the lower bound, is also equal to negative 2. For the upper bound, we can have 4, 5, 6.5, and so on. However, our M max, or the maximum value of M, does not exist because 4 here is not part of the set. But 4 is considered to be the supremum because it is the least value of all the upper bounds. That will be all for my discussion. Thank you very much for listening.